conservation law when the Euler-Lagrange equations hold. So now in quantum field theory, the Euler-Lagrange equations do not hold. And this has always, I think, been a tension in the efforts to understand the application of Noether's approach to field theory in quantum field theory. So roughly speaking, you can say that the work of Batalin-Vilkovisky extends the conservation laws of Noether off shell. And I'm not going to try to explain that statement today, but suffice it to say that there are error terms in the conservation laws that are instances of the Euler-Lagrange equations, the Euler-Lagrange functionals that are set to zero in the Euler-Lagrange equations. And Batalin-Vilkovisky found a consistent way of incorporating that into the formalism in such a way as to clearly give the right extension of the conservation laws of shell. So their work, following earlier work in the 70s, the BRST approach to symmetries in classical and quantum field theories, they had the idea of expressing all of the gauge symmetries and other symmetries of a field theory in a single equation, their classical master equation, as they called it. And I think most of us here know what a Moret-Cartan equation is in a differential graded Lie algebra. I kind of hope so. It's not important if you don't, because I'm going to be just writing out explicit equations. But the Batalin-Vilkovisky classical master equation is in fact a Moret-Cartan equation. And in fact, it has a lot of similarity to the equations governing a Poisson tensor. So another aspect of Noether's work, which is in some sense defective from a modern perspective, is that she works with functionals, which are the integral of local expressions over some region of spacetime. And so she's always working modulo total derivatives. And this makes it difficult to incorporate the study of boundary conditions into her formalism. So I'm not an expert on the history of Noether's field theory, so I'm not sure. It's possible that there have been other efforts to incorporate boundary conditions into Noether's work. I know we have a lot of experts here, but I'm just going to forge ahead with my own perspective, which is that a Russian general relativist called Soloviev found an extremely simple way of incorporating these terms which we are integrating out because they're total derivatives, incorporating them back into the formalism and keeping track of them. And his motivation was precisely that he was interested in studying general relativity in spacetimes with boundary, which, as many people here will know, has in fact become a topic of importance in current physics research. So what Soloviev did, I'll give some equations later to just show you literally what he does, is so Gelfand and Dickey had earlier introduced Poisson brackets or analogs of Poisson brackets on functionals in the context of the study of integrable systems. So they were studying the KdV hierarchy, and they introduced these Poisson brackets in order to understand the commuting Hamiltonian flows. So what Soloviev does is he lifts these Poisson brackets of Gelfand and Dickey to be Poisson brackets on local expressions. So no longer integrated expressions, functionals, but now the actual local densities form a graded Lie algebra. So the important thing is that Solovyev's bracket continues to satisfy the Jacobi relation. So this is where my talk diverges from last week's talk. I'm not going to be talking about L-infinity algebras, properly speaking, today. I'm actually going to just be able to stay in the world of differential graded Lie algebras, and instead I'm going to be generalizing my differential graded Lie algebras in almost the opposite direction. I'm going to give my differential graded Lie algebras curvature. And that curvature is going to express the general covariance of my models. So that's the last aspect of Noether's approach, which I find very difficult to understand, that according to Einstein, general covariance is an extremely important principle of physics, that the theories you write down should not depend on the choice of a coordinate system on your world sheet. So this essentially general covariance is, and then I should say then, gravitation becomes some sort of gauge theory with respect to the diffeomorphism group of the world sheet. So this effort to carefully express the general covariance of the theory, somehow, I think this may be the most contentious part of my talk. This whole introduction is a little bit polemic. Somehow it's really hard to incorporate that gauge invariance under the diffeomorphism group into the formalism. And I think that traditionally it was approached in a very similar way to other gauge symmetries. But what I'm trying to argue in today's talk is that analogy is only good up to a certain point, and that ultimately, I think it calls for a slightly different mathematical treatment to understand the diffeomorphism symmetry, gauge symmetry, and gauge symmetries in the target. So what I'm going to explain is that there's a modification of the classical master equation of Batalin-Vilkovisky, which is a Moret-Cartan equation for a curved differential graded Lie algebra. And I don't know, I'm hoping that it will be a useful technique in the future. But today's talk is simply going to be to present some toy examples. Okay, so that's the end of my polemic. Are there any questions or arguments or comments? Everyone agrees with me. Okay, or I've lost you all already. I don't know where I'm a bit anxious. Okay, so most of the results of this talk, except the final slide, are taken from this paper, which is in Letters in Mathematical Physics. So you can, there are even further techniques in that paper taken from Sullivan's work in rational homotopy theory in order to glue these local results from this talk into a global theory. But enough's enough. I'm just going to talk about the local results on a coordinate patch today. Okay, so first some mathematical background. If you like, the basics of the theory that we're working on differential graded supermanifolds. So it took me a while to understand this concept because as mathematicians know, when you have a grading, a Z grading, the coordinates develop a parity. The coordinates of even degree are even with respect to the Kossel sign convention, and the coordinates of odd degree are odd with respect to the Kossel sign convention. But on a supermanifold, some of the coordinates are already odd, and those are still graded by grading 0. So the point about graded supermanifolds is that the Z grading of the coordinates is independent of the even-odd parity. So that's why it's important to work with graded supermanifolds so that you can incorporate fermionic fields into your theory. So just for those of you from a more physics background, the degree that I'm talking about, physicists call it the ghost number, and it's cohomological for us today. My differentials will all raise degree by 1. And the parity is referred to by physicists as the statistics. So even parity or parity 0 is called bosonic statistics, and odd parity is called fermionic statistics. But this is purely a dictionary and doesn't, we're all talking about the same thing. So,
sorry, is it bigraded then? Or, I mean, is it totally independent?
Effectively, yes.
Bigraded?
Yes, it's bigraded. It's graded by the Z direction, and it's graded by the parity direction, yes. But it's not graded, it's not ZZ bigraded, it's ZZ mod 2 bigraded, okay? And then, so there's, you can take the cotangent bundle of a graded supermanifold, and you can shift the vector space fibers, the cotangent fibers, up and down by degree. And this bracket -1 notation means to shift them down in degree by 1. It's Deligne's notation, and it's very confusing. I was amused once to see him give a talk in which he had to do a little calculation on the side of the board to work out the sign of his own notation. So I think he found it as confusing a notation as the rest of us. Anyway, when the dust settles, this shifted cotangent bundle has coordinates, the original coordinates of our graded supermanifold, and some new coordinates which are, if you like, Darboux. They complete it to a canonical coordinate system. They're the, what are they called? Canonically conjugate coordinates. These are called, in physics, the anti-fields. If the original fields, the psi alphas, are the fields of the theory, then the psi pluses are the corresponding anti-fields. And they have degree or ghost number equal to the negative of the ghost number of the field -1. So if you start with a physical field, that's a field of ghost number 0, the anti-field has ghost number -1. And if you start with what's called a ghost, which has ghost number 1, for the rest of us, those are something like the generators of Lie algebra cochains. So you can think of those as some sort of Chevalley-Eilenberg construction. They'll have ghost number 1, and their antifield has ghost number -2. The parity of the antifield is the reversal of the parity of the field, okay? So I'm going to be doing variational calculus today, and until the last couple of slides, I'm going to focus on the one-dimensional case. So this is barely field theory, it's really mechanics, because we just have a world line with the parameter t. Nevertheless, it already enables me to explain the idea of general covariance. The general covariance will be in the parameterization of the world line, which I think is already an important issue in the application of Noether's work to even just Lagrangian mechanics. So we should think of the fields as being functions of this independent variable t, or if you like, we're studying the path space of this shifted cotangent bundle. So in the variational calculus, we work with the jet spaces. This was all explained last week. So in some sense, I can rush over this slide, but I of course shouldn't do that because I'm not even certain that everybody here today was here last week. But basically we introduce a kind of, well, it's a formal graded supermanifold called the jet space of maps from the line to our shifted cotangent bundle. And I'm just going to understand it in terms of its coordinates. These coordinates are essentially the Taylor coefficients around 0 of my fields. So I'm really just looking at fields which are formal paths in the shifted cotangent bundle. And functions on this space I'll denote by O sub infinity. The infinity because it's the infinite jet space. We're taking not truncated Taylor series, but full Taylor series. And so these are promoted to just being independent coordinates on this formal manifold, formal supermanifold. So I'm going to be studying vector fields on the jet space, or in other words, graded derivations on this function space. And to do that, I'm going to, here's a frame of the tangent bundle of the jet space, just differentiation with respect to these coordinates. So I'll abbreviate those. So this slide should be kept visible for the rest of the talk. But if you have a pen handy, jot down these formulas, because these vector fields will come up over and over again. Okay, this frame of the tangent bundle. I hope it's clear. So just remember that if there's a subscript alpha, we're doing differentiation with respect to one of the Taylor coefficients of the fields. And if it's a superscript alpha, so conjugate, then we're doing differentiation with respect to Taylor coefficients of anti-fields. Okay? So that's my introduction to variational calculus, more or less. So the key role in the whole subject is played by infinitesimal time translation, which is this explicit vector field. Okay? Now, this vector field is an infinite sum, and this is where the fact that we're dealing with some sort of formal supermanifold is important, so that on any given function, this infinite sum is actually just a finite sum. So in fact, the functions on the jet space only depend on a finite number of the coordinates. So, so this is meaningful mathematically. So it's important to consider on the jet space precisely those vector fields which commute with time translation, and those are called evolutionary. And we'll see many examples of such vector fields. So now we come to the key definition in the subject, that the functionals are precisely functions on the jet space modulo total derivatives. So, well, I should say that here I'm simplifying by only considering functionals which are t independent. They don't have any explicit t dependence, but you can in fact introduce functionals which have explicit t dependence as well. I'm leaving that out of today's talk. So I'm going to adopt the abbreviation that if I have a density f, I've left the dt out of the notation, then its integral is a functional. All right? So this integral sign basically just means take the coset with respect to the image of this vector field. It's a very algebraic approach to calculus. And we have the variational derivatives, or Euler operators, given by the usual formulas that I think everyone here will be familiar with. And these operators vanish on the image of the time translation. So they're invariant under time translation. So they actually define linear operators from f to functions on the jet space. And so we have the variational derivatives for the fields and for the anti-fields. Okay? And so this is the Batalin-Vilkovisky anti-bracket. This is the primary object of study in the classical Batalin-Vilkovisky formalism. I'm not going to be saying anything about the quantum formalism today, despite my abstract, because of course I'll run out of time. So so let's look at this formula. If the psi alpha and the psi plus alpha were replaced just by some Darboux coordinate system on an ordinary symplectic manifold, we would get one of the ultra-local Poisson brackets of Gelfand and Dickey. So there are actually, I didn't put those references in my slides, but there are two excellent references for the classical subject. One is the book of Peter Olver in the Graduate Texts in Mathematics series, and the other is a monograph by Manin, which is, I think it's in the series Soviet Mathematics. So it was in fact translated into English, and it's a complete monograph on the variational calculus and integrable systems. So it in fact has some proofs which are left for exercises in Olver. So it has some, it's quite a useful reference. Anyway, if you look at the structure of this formula, you see that F and G are functionals, or rather, I want my Poisson, my antibracket, to only depend on F and G modulo total derivatives. And so, fortunately, the variational derivatives have exactly that property. And each of these variational derivatives is a function back on the jet space. And then, so I can take their product on the jet space, and then take the coset with respect to the action of the vector field curly D. The signs are a bit painful. I've written them out in a convention in which my derivatives are always from the left. Batalin-Vilkovisky have simpler formulas in which the derivatives are taken from the right and from the left, respectively. But then you have to introduce what you mean by differentiation from the right. And I've avoided that by putting these explicit signs in. Okay? So don't take the signs too seriously unless you're actually going to do calculations. Like check my, I've written a lot of formulas later in the talk without checking them for you. So if you want to go check them, you'll need this exact collection of signs. So now I come to the main point of the talk. There's this explicit element. I should have written a sum over alpha here, but I've used just here the Einstein summation convention. This element lies in the center of the Batalin-Vilkovisky antibracket. I'd be very interested, given that there are some experts on the Batalin-Vilkovisky formalism here, if anybody knows of an earlier reference than my 2019 paper for this observation, that there is this central element, and I don't think there are any others. It's somehow an important question always if you're given a differential graded Lie algebra, a Lie algebra, to find its center, and here is the center. So when you have a central element, you can perform a construction which is to curve your Lie algebra. What you do is if for those of you who were, for example, here last week and learned what an L-infinity algebra is, so in an L-infinity algebra, we have a bracket of arity, any positive integer. So there's a linear bracket, which is the differential, a bilinear bracket, which is the Lie bracket, a triple bracket, which is some sort of homotopy for the Lie bracket, and so on. But you can also go downward, and you could introduce a zero arity bracket. In other words, an element of the graded Lie algebra, of the differential graded Lie algebra, and that will be an element of degree 2. So I want to make this D, which has this element actually, well, it's a bit tricky because this bracket has degree 1. And so actually, if I want to curve this, a graded Lie algebra in which the bracket has degree 1, it turns out the curvature also has degree 1. And so this D has, if you followed, it has degree -1. It's homogeneous. And a way to make it something of degree 1 is to multiply it by a formal variable of ghost number 2.
Ezra.
Yes.
Hi, Anton. I have a short question. So
Yeah.
this under the BV bracket, does it generate the time derivative, or right? It generates some sort.
Well, the point is the time derivative is 0 because I'm working with functionals.
Yeah, on the, oh, okay. So
yeah,
that's why
wait till slide, I don't know, 15 or something, and I'll answer your question. Okay.
Okay, I'll be patient.
Okay. There's also a question.
So Alan asked a question.
Ezra?
I just opened the chat. I'll keep the chat open in future. So Alan asked a question, is this D the de Rham differential? And the answer is in some sense no. Because there's no dt yet. So I don't have 0 forms and 1 forms. But they're also on the same slide that answers Anton's question, I'll answer Alan's question. Okay? So these are 2 sides of the same question. So, but what I have here is if I have a central element in a graded Lie algebra of degree 2, then I can just nominate it to be central curvature. So it's some sort of projective differential graded Lie algebra with vanishing differential. Anyway, it's a formal construction, but it deforms the Moret-Cartan equation. The point is that all of the brackets of the L-infinity algebra enter into the Moret-Cartan equation, and if you have curvature, then the curvature is an inhomogeneous term in the Moret-Cartan equation. So the, oops, my mouse. Well, this kind of answers both Alan's and Anton's questions, I think. I forgot about this slide. So if you think of D as, if you modify D by multiplying by a time-dependent coefficient, then that somehow generates the vector field associated to that coefficient. Okay, so underlying what I'm doing, but I haven't brought it out in the mathematics, is that the action of the Lie algebra of diffeomorphisms of the world line is closely related to this element D. But right now I'm just doing a very toy version of a toy version. So I'm not really emphasizing the full diffeomorphism group, but only translations. Okay, so I want to introduce an explicit solution of the Batalin-Vilkovisky formalism so that I have an example to talk about. And this is going to be something which many people here are probably familiar with. There's a type of classical field theory called AKSZ models. And they're associated with targets which are shifted graded symplectic supermanifolds. But I'm just going to do the one-dimensional case, which is hardly ever mentioned, and which has certain special features. And so I'm now going to assume that I have a symplectic structure on M, on my graded supermanifold. Now, so the grading of the symplectic form is going to be 0. So the Poisson brackets on my graded supermanifold will have ghost number 0. But in order to perform the AKSZ construction, you need to choose a 1 form whose differential is the symplectic form. I don't think this point is emphasized particularly in the usual treatments, but it's an essential piece of data. And I want to remark that in the case where we're just dealing with an ordinary symplectic form of ghost number 0, like on this slide, then the choice of nu, what I'm calling a Liouville form, this choice is also can be thought of as a connection form on the pre-quantization line bundle. And so in some sense, so it's actually my feeling that that symplectic geometry is really the study of the pre-quantization line bundle with an explicit connection on it. But maybe that's a minority view. So to me, this structure is almost the correct definition of a symplectic manifold, but that's probably unpopular. Anyway, so I need my
Ezra, I don't know if you can still see the chat. There's another question in the chat by Alejandro Cabrera.
No, I didn't introduce Hamiltonian vector fields. So the question is, isn't the Hamiltonian vector field 0? So Hamiltonian vector fields are not defined in variational calculus using the Poisson bracket of Gelfand and Dickey. They're defined by a different formula. They're the evolutionary vector fields whose coefficients are the variational derivatives of the functional. So I don't have time to explain that, but it turns out that these, one way to see it is the following. So Poisson bracket with D is not a vector field. It's an infinite order differential operator. Because the Euler operator is an infinite order differential operator. Look at it. You see, curly D is a first order. Curly D is a first order differential operator. It's a vector field. So the term for K here is a degree K+1 differential operator. So this whole thing is an infinite order differential operator. So you can't obtain in variational calculus vector fields using this formula. So you have to find them elsewhere. And well, you can. And if you read Manin's book, you'll learn everything about that. But in fact, it's explained also in the paper that I gave the citation of earlier. If you want, I rediscovered it actually. I didn't know that there was this whole theory. So yeah. So anyway, back to my Liouville manifold. So I have to assume now that that my two form is symplectic, so that I can invert it and obtain a Poisson tensor. So this may be a disappointment to some people, but now I write the following two functionals. I've left out the integration sign, unfortunately. So so I have S0. That's going to be the action of the theory. So this is an AKSZ theory, a very limiting case of an AKSZ theory, but if you bear with me, I'll produce all the AKSZ theories in a second. So this is an explicit expression, and notice it only depends on the fields, not on the antifields, okay? Which may be a bit of a surprise to people, but if you like, I can discuss that more after the talk. If somebody remembers to ask me why there are no antifields in my action. And then this S1 is basically, what we're going to see is it's going to be the Batalin-Vilkovisky Hamiltonian for the action of the diffeomorphism group on the line. So it's this S1, which is the new concept in this talk. It's the gadget which will express the general covariance of the AKSZ model. So essentially, this slide is the most important slide in my talk. And what I want to emphasize is that although the AKSZ action doesn't depend on having a symplectic form, if you look at the formulas in the AKSZ model, they only depend on having a closed two form, which of course locally will be a differential of a one form. But they don't depend on that two form being invertible. But in order to express the general covariance of the model, we need that the two form is symplectic. That's, in some sense, that symplectic geometry can be viewed as the pair of this one form and this bivector. That's my contention, somewhat contentious contention today. Okay. So I'll just leave that slide up for a second. Oh, I've got a question. Yeah, go for it.
Just a very stupid question. This S1, what is its grading and what is its ghost number?
Very good. So, yeah, very good question. So because psi alpha has ghost number equal, let's say that psi alpha has ghost number n. So nu alpha has to have ghost number negative n. And therefore, omega alpha beta has ghost number, oh dear, negative n minus m, where alpha and beta, where n and m are the ghost numbers of alpha, psi alpha and psi beta. So pi alpha beta has ghost number m plus n. Right, yeah, n plus m. And so when you work it out, this has ghost number -2. Okay, did you follow?
Sure. I mean, I didn't follow, but I believe you.
Yeah, so it's homogeneous and it has ghost number -2. So that's a great question. Thank you for asking, because S0 has ghost number 0 and S1 has ghost number -2. That's very important to my talk.
What about the parity?
It's even.
Okay, thank you.
Yeah. So that's because the parity of pi alpha beta is the sum of the parities of psi alpha and psi beta. And so these guys have reversed parity, but there are 2 of them, so that cancels. Okay, it's a little bit complicated. I think the basic equations of this talk are quite simple, but checking all the details ends up being a little bit technical, unfortunately. So here's my main result in the first part of the talk, that if I take S0 plus u times S1, where u is just a formal parameter of degree 2, then S sub u satisfies the curved Moret-Cartan equation. And my contention is that essentially this expresses the general covariance of the AKSZ model. So when you expand this in powers of u, this comes down to these 3 equations. So this is the classical master equation of Batalin-Vilkovisky. This is my new equation. And this expresses basically that my functional S1 is the generator for the flow along the world line. And finally, this is well, those of you who do homotopical algebra will know why this is here. So, okay, I'm being a bit obscure. If you think about Cartan calculus, you have that iota of a vector field, contraction with a vector field twice is 0. And so this is somehow analogous to that. Okay, so just once we have a solution of a Moret-Cartan equation, you can gauge it. This was invented by Drinfeld, the idea of gauging Moret-Cartan equations. In the usual theory of differential graded Lie algebras, Moret-Cartan elements have degree 1, and we gauge them by elements of degree 0. Now, because the Batalin-Vilkovisky antibracket is a Poisson bracket of degree ghost number 1, the Moret-Cartan elements have ghost number 0, and we gauge them by elements of oh, that's a misprint, of ghost number -1. Okay, I think. No, maybe. Yeah, ghost, that should have been, sorry, we're not yet up to the gauging. Yeah, so no, this is not a misprint. I now want to, my symplectic, so M now is a symplectic supermanifold. And I want to make it into a differential graded supermanifold by placing on it a Hamiltonian vector field of ghost number 1, whose square is 0. That's what a differential graded supermanifold is. And in order for that equation that the Lie bracket of the vector field with itself vanish, we need that the Poisson bracket of our function of ghost number 1 with itself should be 0. So this is with respect to the Poisson bracket of d nu, the symplectic form, or rather with respect to the Poisson bracket middle pi. So what I do is I take U inverse W, that has ghost number -1, so that's the right ghost number to gauge the Moret-Cartan element in my curved graded Lie algebra. So there's some explicit formula for how you can twist Moret-Cartan elements by gauge parameters. Notice though, this gauge parameter is singular. It involves U inverse. And normally you certainly can't gauge by something which has a pole in U. But it turns out that because of this formula that W Poisson W is 0, the terms which would have created negative powers of U cancel. And so the gauge transformation is well defined. And what you end up with is that S1 does not deform, but S0 deforms by this expression. And this is the AKSZ model with symplectic form d nu and with potential W. So this is the most general AKSZ model in one dimension. And it continues to satisfy the curved Moret-Cartan equation. Okay, so that's a good place for me to ask if anybody has any questions, any more questions.
Yeah, I have one more question. Yes. So how is it for all these to hold? Is there some condition on how W on the bracket of integral of S naught and integral of W?
That's no, that bracket is 0.
Why?
Because S naught and W only involve fields, not anti-fields.
Oh,
if you look at the explicit formula for S naught, it doesn't actually have any anti-fields in it.
Okay.
So it's actually it actually is pulled up from M. It doesn't involve the cotangent bundle. It's a rather bizarre feature. So you're at this point really upset with. You're the only other person here that I know who's written.
But this means that S naught automatically satisfies the classical master equation, right? Like trivially.
It's rather trivial, yes.
Okay.
Yeah. But now, once you twist by W, it's no longer trivial. Because, yeah, so that's not clear from what I've written. But this second term does involve anti-fields. So that's where all the complication of checking that SW, this equation, this classical master equation is not trivial. So I've trivialized the verification of the master equation. That's the point of this slide. The reason that this equation, this master equation holds is that it held for S naught, but it held for S naught for trivial reasons, and that SW is a gauge transform of S naught. Does that make sense?
Yeah, thank you.
So it's a slightly bizarre perspective on AKZ, but one that I'm fond of. Now, and you just reminded me that you're the only other person here who's written about one-dimensional AKZ models. So, yeah. So, so now I have barely enough time, just enough time, I think, to talk about the Soloviev bracket. So I'm going to try now to explain what you have to do if you want to keep track of all the integrations by parts. So this is a very vague remark, is that there's a large body of work now by Kataneo, Menyov, and Reshetikhin, which discusses the boundary value problem for classical field theories and for quantum field theories, and then continues to discussing corners. And roughly speaking, I'm attempting to understand similar issues, but without introducing manifolds with corners into the discussion. Somehow, I'm just trying to keep track of lower degree differential forms in my densities, which are ready to be integrated over lower or higher codimension cycles in the world sheet. So that's a bit vague, but I'll just forge ahead and explain the formalism in this toy situation. Oh no, there's a misprint here. Okay, so I didn't proofread my slides. So now we get to the de Rham complex. So of course, so think of the functionals as a sheaf over my world line. So of course, that's a bit hard to do because I've told you my world line is actually the formal completion of the world line at the origin. So, okay, no problem. Think of it as a sheaf over that formal scheme. No problem. Okay. So it has a resolution by the Poincare lemma. And here there's the misprint is that this D should be over the arrow. So this is the de Rham differential. The de Rham differential is, of course, time differentiation times dt. Okay. So I'm going to take this complex and replace F by this complex and lift the Batalin-Vilkovisky anti-bracket to this complex, and that will be the Soloviev anti-bracket. Soloviev's work is in a much more general situation, but it turns out that once you understand the anti-bracket case, you can recover all of his work with somewhat less trouble than he put into it. Okay, so I'm going to introduce the notation double parenthesis for the lift of the Batalin-Vilkovisky anti-bracket to this complex, my de Rham complex. So this, by the way, if I understand right, this is the horizontal de Rham complex from the talk last time in the very special case of the real line crossed with the shifted cotangent bundle. Maybe that we can discuss that after the talk, if I've understood that correctly. So this is a bit too complicated, but basically I'm lifting the anti-bracket so that F and G, their anti-bracket produces the one form component of the anti-bracket. That is, anti-bracket of densities is again a density, and the lower order terms contribute the lower order terms on the right-hand side. So focus on this first line. This is the key.
Ezra,
yes.
Luca just wrote in the chat answering your question that yes, it is.
Oh, it is. Okay, so we don't have to discuss it. Okay. So this is the key idea of Soloviev, and it is a little overwhelming. But what is remarkable is that it satisfies the Jacobi relation. So it defines a graded Lie algebra. I don't have a good explanation for why that's true. All I know is that he proves it, and I checked it, and it is right. This is a much simpler situation than the one in his paper, although he doesn't consider the graded supermanifold case just the case, of manifolds, but he's considering the general Gelfand-Dickey brackets, whereas I'm only considering what are called ultralocal Gelfand-Dickey brackets, and that simplifies the proofs. But I can recover all of his results because Gelfand-Dickey brackets are actually derived brackets for this universal anti-bracket. So, okay, so I hope people have somewhat absorbed what's going on here. What we've done is we've taken the original expression involving Euler derivatives, the Eulerian operators, and we've done all the performed all these integrations by parts. So we've moved the kth derivatives with respect to t from this factor and moved it by integration by parts over to the right factor. And it turns out that if you do exactly this prescription, then you get something that satisfies the Jacobi relation. So if at least I advertise this single point in my talk, then I'll have achieved my main goal. because I really want this Soloviev bracket to be more generally known by the Poisson community.
Ezra?
Yes.
A possibly stupid question. If I forget about F tilde and G tilde, right? If I only focus on F and G, right? So this that's going to be still a Lie algebra, right?
Absolutely.
What is it? If it's a simpler object.
That is Soloviev's Lie algebra. The extension to de Rham is all my work.
Oh, okay.
Yeah.
Oh, okay.
Yeah. So so I'm partially inspired by just trying to do calculations, and also partially inspired by the fact that, if you like, these tilde terms are, in my view, expressing the BFV side of the work of Cattaneo-Mignov and Reshetikhin. That's one of my contentions here. But as you see, I'm focused on just writing down one formula after another. That's sort of the way I do mathematics. So perhaps I'm just trying to let the formulas speak for themselves, which is a bit hard on a first exposure, I guess.
Can I ask also? So you mentioned something about that you've avoided manifolds with corners, and but if you have corners, this formula, some form of it still holds, or there would be some kind
of... I mean, what I really mean is that first of all, I think physicists, maybe I'm going out on a limb here. So I'm thinking about, when I say physicists, I'm thinking maybe more of the sort of people who are doing topological field theories with defects. And instead of thinking about manifolds, they actually think about hypersurfaces. Instead of thinking about boundaries, they stratify their manifolds in a more general fashion. So I think that instead of focusing only on boundaries, we can also be thinking about hypersurfaces that are somehow have two sides. Or even, I think people study foams in which you have hypersurfaces with more than two sides. So I think that the extension to stratified spaces is what this is calling for. And I think it's ready to be generalized to stratified spaces, but the problem is that I'm not ready. My problem is that this depends on a coordinate system on the world sheet. And part of the purpose of my talk is to try to understand how the Soloviev bracket changes when you perform a change of coordinates on the world sheet. But I'm not yet ready to glue the whole thing together. This is still a local theory on my world sheet. So I'm not quite there yet. So, but we could discuss local models for foams, and I think this would work just fine in that setting. Okay. Thanks for that. That answer, I had never thought about that before. So that answer was utterly improvised. So if we have time after my talk, maybe we can return to that if you're interested, and we can, and maybe some of the people here can pull it apart. Okay. So now I'm going to try to lift my curved differential, my curved Lie algebra structure from the first part of the talk to this resolution, this de Rham resolution. So I have to lift the curvature, and then I have to introduce a differential. So the lift of the curvature depends on the assignment of world line dimensions to all the fields. And then the antifields will have conjugate dimensions. And here I'm using the convention that functions have dimension 0 and one forms on the world line have dimension 1. So some of you will think that this looks a little bit similar to what we do in conformal field theory. And that's because conformal field theory is also a one-dimensional theory. It's just that the world sheet is a one-dimensional complex manifold. So this is, in some sense, one-dimensional real conformal field theory. So I introduce this lift of D. You see that it has the, as as the main part of the density is what we had before, but I add this total derivative depending on the dimension. And then here's an explicit differential which satisfies that its square is u times this. It's the bracket, it's the anti-bracket, the Soloviev anti-bracket with respect to this curvature. So in that way, I get a curved differential graded Lie algebra. So this is sort of the culmination of the talk. This was the main, in some sense, my main discovery in my paper, that I could find this somewhat confusing. This is a very confusing operator, I will say. But, oh, yeah. So what, okay, but I should say that these two terms exchange the 0 form and 1 form on the world line. So this is the de Rham differential. And so now I answer Alan's question. Finally, we see the de Rham differential, and you see it plays a role in a formula for the square root of the curvature, if you like. And it takes the 0 form piece and puts it in the 1 form slot, whereas the other term takes the 1 form piece and puts it in the 0 form slot, but multiplies by u. So obviously, this is somewhat, inspired by equivariant, the Cartan differential in equivariant cohomology, but it is definitely not such a differential. It's a variational calculus object, and I think it's new, and I think it's sort of interesting to study its ramifications. So now
somehow the first piece of this formula depends only on F tilde, and the last, which is the huge summation thing, only depends on F.
Only on F. That's right. Yeah. So it's just like the Cartan's thing takes. It has two terms. One is the de Rham differential, and the other is an iota, which reduces degree by 1. So you have two terms. One raises degree by 1, and one reduces degree by 1. And I have the same thing here. So
well, you say lift the curvature.
I mean, lift it from F.
No, I'm just questioning notation.
Oh yeah. I mean, by lift, I mean I've stripped off the integral sign.
Okay.
I'm looking at the density. This should have a dt on the end. That's a mistake.
So is UD the lift or the original that had to be lifted?
Oh no, when I put an integral sign, that's taking a equivalence class. I'm integrating means throw away total derivatives. So now I'm putting the total derivatives back. Okay. That's what I mean by lift.
Yeah, no, lift wasn't the question. The question is, you have different notation for what's to be lifted versus the lift. Same notation, UD?
Oh, I see what you mean. Yeah, I've used the same notation. Sorry.
Okay.
Yeah. Okay. I think that many mathematicians, I mean, physicists do that more than mathematicians. It's got a name in computer science. I think it's called, I forget what it's called. Yeah, so where functions, their meaning depends on the type of what you're applying them to.
Okay.
Yeah. Okay. So so here's my curved Morikawa equation. So if I moved the curvature over to the left-hand side, I would have a 0 arity term, which is the curvature. Then I would have the 1 bracket term and then the 2 bracket term. So that's the equation, and here's the solution. So it looks very similar to what we had when we took functionals, but there's this additional term in S1, which is a 0 form piece. Okay, I've run out of time, so the details of this formula are not really important. It's that it solves the Morikawa equation, which is the key, plus that it's practically the same as it was in the integrated case. But this is the whole effect. If you like, what I'm saying is this is the BFV, or the boundary effect of general covariance, expressed in a curved Morikawa equation. And I want to add that this equation is by no means a triviality. it takes me like a day to verify that, or more, to verify this equation for this input. So don't try to do this at home. Or if you do, set aside a long time, because it really is a very long calculation to get it straight. Okay, so so in some sense, I believe that I've discovered something new about Poisson geometry, although I'm not entirely sure what.
The calculation, is it just kind of long, or is there some kind of non-trivial ideas involved?
There's there's no non-trivial ideas, because I have no equation whatsoever to work with, except that my symplectic form is closed, that my Poisson bracket is a Poisson bracket, and that they're inverses to each other. But I will say, just the very fact that the closure of the symplectic form is equivalent to the Poisson identity. Notice those are both Moret-Cartan equations. D omega equals 0 is a Moret-Cartan equation in an abelian differential graded Lie algebra, whereas pi bracket pi equals 0 is a Moret-Cartan equation in the Schouten algebra, which is a graded Lie algebra with vanishing differential. So the fact that this inversion procedure, taking omega inverse equals pi, takes a Moret-Cartan equation into a Moret-Cartan equation is a very non-trivial thing. And this is somehow closely related to it. So I don't use anything beyond that, but it's not simpler than that. And that's already a full day calculation in my view, practically. So I think I've kind of run out of time. Here are corresponding formulas for the Chern-Simons theory in 3 dimensions, which I worked out for this talk, because I wanted to make sure that my formalism, although I strongly believe my formalism works in any dimension, I wanted to absolutely confirm that. I have a student working on the Yang-Mills case at the moment. So hopefully that will be done in the next few months. So you see that it's very similar. The S0 here is the AKSZ action for the abelian Chern-Simons theory, as written down, for example. I always think of it as being Axelrod and Singer who wrote down the BV formulation of Chern-Simons first. And then S1 is new. In fact, I think new as yesterday. And the twist is also new. And the fact that the twist satisfies that it doesn't produce singular terms is a sort of seat of the pants calculation. So just one last point that I'd like to make is that this formulation of the curved Moret-Cartan equation, I think it extends to higher dimensions, but I don't see any way to incorporate spinorial fields into this formalism, at least at the moment. So that's sort of the major defect at the moment, that general covariance for spinors remains a mystery to me. So thank you very much.
Thanks a lot, Ezra. And now it's, of course, time for questions.
Hi, can I ask a question?
Please go ahead.
I want to make sure if
I can't quite hear. Can you talk louder?
Can you hear me?
Barely.
Barely. A second, let me put...
That's it. That's better.
A second. Is it that?
Early.
Okay.
Can you try?
Ah, that's good.
Okay. So I just want to check if I understand your method correctly. So you start kind of with classical master equation, and you find it can be equivalently written in terms of Moret-Cartan equation, which is flat. And then you discover the gauge action that you can apply on it what you call twist. And then you just summarize from this twisted formula, and you got this curved Murakatani equations.
No, other way around. Sorry, I'm interrupting you. The twisting before going to the curved Murakatani equation, the twist is trivial. It's only because I add that extra term S1 into the action, which is now a solution of the curved Murakatani equation, that that there are non-trivial twists at all.
But yeah, I think I get so anyway, this twist with this additional action, they kind of generalizes the set of classical master equation, but written in different form. So
yeah, this is an idea that I'm increasingly applying, and I'm interested if anybody else has seen it. The idea of looking at singular gauge transformations, which take us nevertheless. So you can imagine having a connection and applying a gauge transformation, which is singular, but the gauge transformed connection is not singular due to some additional equations. This is something which I find myself increasingly drawn to these days. I can't explain it. It's only just, it just happens. But it does seem to be something that occurs throughout AKSZ, if you want to look at it that way.
What's your favorite example?
Well, I think in some sense, Chern-Simons.
Okay.
The idea that, yeah, so this must be, it must be possible to write this more simply, but I haven't yet worked out how. Well, partially because I only found it yesterday. That somehow we can view the non-abelian Chern-Simons as a singular gauge transform of the classical. So if you take the solutions of the curved classical master equation, that there is a gauge transformation that takes the abelian Chern-Simons to the non-abelian Chern-Simons, but that gauge transformation is singular.
So, hi Ezra.
Hi there. I see you, continually pressing your unmute, but yeah.
So, by the way, I also have the formula you wrote for Chern-Simons when we tried to write equivariant Chern-Simons.
Oh,
right.
Great.
What did you want to tell? What did you want to tell people about our paper in relations to what you are doing?
Oh, sorry. Yeah. So that was at the end of the abstract. Yeah.
Right.
So Maxim has written a paper. Was it last year or the year before? I forget.
I don't know. Last year, yes.
I think it was last year. Maybe April or something. I only learned about it a few months ago, though. I learned about it at the conference in Sao Paulo, I think. Did I? No, in the conference in Scalea. Yeah. So it takes the quantum version of this. So it turns out, as you can see, Maxim, I ran out of time. So so the quantum master equation involves, so if we go back to the shifted cotangent bundle, so the shifted cotangent bundle, we can look at Lagrangian submanifolds in it. And so if I remember right, the condition is that capital D should vanish on the Lagrangian. Is that right? I think that's your additional equation. And then you're able to show that and this is in the formulation of Kudavedian or maybe you don't do this in your paper, but maybe I reformulate your paper in Kudavedian's language, or do you already do that? In terms of half densities. But I think it is very elegant to this. In short, we have to introduce a complex of half densities on the shifted cotangent bundle, which is actually just, I guess, top forms on M. I'm sorry, integration forms on M. And maybe this isn't appropriate for the general questions, but for the discussion afterwards, if you can stick around.
Okay.
It's a bit of a long, bit of a long story, but yeah. So Maxim was trying to advertise that there is a quantization of this story, and the paper. Did I give the list of authors? And I think that it's Bonecki.
At least you have to cite people who in the chat. It's Cattaneo, right?
Well, I was going to say, I'm trying to alphabetize. Bonecki, Cattaneo, and then Chin, is that?
Q.
Sorry?
Q.
Oh, Chu. Okay, and you. Yeah. So, yeah, so I think that the paper is actually uniquely determined by the list of authors, which is in the abstract. Yeah. But if you like, I can put it in the final version of the slides. Yeah. So
one question about the AKSZ part. Your example happens to be that, but is it at all necessary for what you were doing?
No. So so absolutely not.
Good.
So first of all, if you have an explicit coupling to diffeomorphism ghosts, then you can simply take S1 to be the ghosts. So that's for starters. But there's a much more complicated story, which a student of mine did for his thesis. So you can find that in a joint article we wrote in Advances in Theoretical and Applied Mathematics. That's a paper with, oh my God, I'm sorry, I got out of bed the wrong, okay, anyway. I'm blanking out my own student's name. It's so embarrassing. This happens when you reach old age. Yeah.
We can crop this out of the final video.
Well, I was up late last night doing slides. Oh dear. Oh, can we move on to the informal part, which isn't recorded? Anyway.
Yes,
so what
sure.
I wanted to say is that there's another model which fortunately doesn't have. Well, one thing I remember. Okay, I'm sorry. There are many different issues that I'm trying to talk about simultaneously. So this is also a model in one dimension called the superparticle. Now, this model doesn't involve spinors on the world line. But I should also mention that in one dimension, we've handled spinors, because spinors are simply fields of dimension a half in one dimension. It's only in higher dimensions that spinors become different from tensors, or much more different from tensors. So the one-dimensional theory does have some special features. But in any case, the superparticle does not have spinors on the world line in it. It only has functions and one forms. But it instead takes values in superspace in 10 dimensions. And this theory has a topological term. That's the part I've left out from today's talk. So you can upgrade all of this to handle topological terms in the target, or if you like, differential characters. And what he showed in what I think is a tour de force is that is also it gives a solution of the of this equation, but it's actually a Kaluza-Klein reduction of a nonlinear sigma model. So it's very much a dynamical model. It's not a topological field theory at all. It's an insanely complicated theory, the superparticle, beloved of string theorists as a toy model.
All right, any further questions?
Can I ask, maybe it's best to kind of indeed move on to the more formal discussion. But I was just going to ask if you could maybe repeat and maybe elaborate a bit more on what you were saying about these single-stage transformations. Like in what way
yes,
the singular
yes. So I wonder if I can write on the. So this is going to be risky. The problem is that the camera is on my computer. I haven't yet bought a camera. So if I detach the tablet from my computer, the camera.
What kind of tablet is it?
I'm sorry?
What kind of tablet is it?
Oh, I have a Surface Book.
Oh.
So
one thing you could do is you could connect to.
Oh, hang on! I know what I'm going to do. I know what I'm going to do. Sorry, I'm going to input the paper. I wonder if that's the paper. Yeah, no, that's the wrong paper. Oh, it's one of these. Maybe it's that one.
That's the one you've just opened, no?
Oh, then maybe it's that one. Nope. Oh God, this is getting embarrassing. You're getting to see all my. Oh. Okay. I'll just open the tech. So let me go back to full screen. There. Okay. So the top line, that's what I would have written with my pen. But so you should think of it as like a conjugation of a connection by a formal gauge transformation. And Drinfeld observed that it's just written by this explicit series. Well, maybe it was already known to certain gauge theorists. If you expand gauge transformations in power series in the gauge parameter. But it's a nice way of writing it. This works in the curved case. That's what I'm using without modification. So even though the differential is no longer has square zero in curved Lie differential graded Lie algebras, you still can use this formula. So the issue is that this formula, first of all, should truncate, and secondly, should have no negative powers of U. And that turns out to be something about derived brackets. So somehow the first term is a differential, and the term with n equals 1 is a derived bracket of y with itself. And somehow the fact that that vanishes is key. And that's exactly the condition in the Aksad model. So it's a sort of, I don't know. Yeah, it's just a series of coincidences at the moment.
Sorry, what vanishes exactly? You said the fact that what vanishes?
Well, in the Aksad model, you need that the Poisson bracket of the superpotential with itself vanishes. And that's exactly the condition that I need here, because I need that some derived bracket vanishes, but the derived bracket in the setting of Poisson geometry is the Poisson bracket.
I have a possibly easy question.
Okay.
So you mentioned this 3D Chern-Simons as an example in the end.
Mm-hmm.
And you also mentioned briefly this 1D Chern-Simons example. So is it like an example of your formalism, and how does it fit?
No, it's an extension. So the formalism I gave in the first part of the talk was really restricted to one independent variable. So you have to, if you have several independent variables, then you have to introduce first of all, you have to introduce the full de Rham complex.
Oh, no, Ezra, I'm speaking about the 1D example. So
the 1D example. I developed I've got to tell you that although you wrote about one-dimensional Chern-Simons, which is an example of this, I had a different example in mind, which was something called the spinning particle, which is the one-dimensional reduction of the NSR superstring. So it's a sort of toy model for superstring theory. It turns out it's an XSZ model. I was very surprised to realize that.
Yeah, but this 1D Chern-Simons, is it an example of your theorem?
Yes.
And there you're...
Oh dear, is it? Yeah, why not? Maybe not. Maybe not, actually. Can I get back to you? Can you send me an email to remind me to get back to you? Okay. Maybe not. Okay. No, hang on. No, hang on. Let's think this through. We can do it. There's only one field, which is the ghost. Because we can
sort it out later.
We can't do it in our heads. Okay, maybe I'm wrong. Okay. But I should say that BF theory is obviously going to be an example of all this. Yeah.
I'm looking if there are no further questions. I would say maybe it's time to thank the speaker again. Thanks, Ezra. And so next week's speaker is Megumi, I believe.
Yes.
Super.
And yeah, are we having an informal part now? I think that's a new tradition that I haven't heard about.
It was impromptu. Yeah, we might. Yeah. I'll start having more time and I'll open sessions earlier and such.
Oh yeah.
Yeah, I've just been.
I want to say that I think if I add up the number of years I've known everybody who was at my talk, I might even reach 1,000. It was really overwhelming.
Probably.
Okay. Thanks a lot.
Yeah, thanks a lot.
Thank you. Yeah. Okay, and see everyone next week.
So Maxim, if I can remark, I was meant to be.
Alberto is here also around.
I'm sorry?
Alberto is also around. Hi.
Yeah, right. I know. I saw you there. Yeah. Maxim, I was meant to be in Stockholm in September.
Well, I meant to be in California.